Exoplanets are planets that orbit stars other than our Sun. The transit method detects exoplanets by observing the dimming of a star as a planet passes in front of it. The radial velocity method measures the wobble of a star caused by the gravitational pull of an orbiting planet. Both the transit and radial velocity methods are used to confirm the existence and characteristics of exoplanets. These detection methods provide valuable data about exoplanet size, mass, and orbital period. The discovery of exoplanets expands our understanding of planetary systems beyond our own. The transit method detects exoplanets by monitoring a star's brightness over time. An exoplanet passing in front of the star causes a slight dip in the star's brightness. The amount of light blocked reveals the presence of the exoplanet. The depth of the dip in brightness allows scientists to estimate the exoplanet's size. The radial velocity method detects exoplanets by measuring the Doppler shift in a star's light. As a planet orbits a star, it causes the star to wobble slightly. This wobble creates changes in the star's velocity, which can be detected. Changes in the star's velocity are detected by analyzing the star's spectrum. The habitable zone, also known as the Goldilocks zone, is the region around a star with suitable temperatures. The habitable zone allows for liquid water to exist on a planet's surface. Liquid water is considered essential for life as we know it. The distance from a star determines whether a planet falls within the habitable zone. Planets outside the habitable zone may not support life due to extreme temperatures. The habitable zone is a key factor in the search for extraterrestrial life. A planet's temperature is determined by its distance from its star and the star's luminosity. Planets too close to their star are too hot to sustain liquid water. Planets too far from their star are too cold, causing water to freeze. Liquid water can only exist within a specific temperature range. The presence of liquid water is a key factor in determining a planet's habitability. The balance between stellar distance, luminosity, and planetary temperature is crucial for liquid water. A planet's atmosphere regulates temperature and protects from harmful radiation. Atmospheres trap heat, preventing extreme temperature swings. A stable atmosphere fosters environments conducive to life. Atmospheric layers act as a shield against cosmic radiation. Without an atmosphere, planets experience drastic temperature fluctuations. Atmospheric composition is critical for maintaining planetary equilibrium. The atmospheric composition of a planet is a key factor in determining its potential habitability. Oxygen, methane, and carbon dioxide are gases that can indicate the potential for life or biological activity. The presence and concentration of specific gases can be used to infer the presence of biological processes. Atmospheric analysis can reveal the presence of biosignatures, providing clues about the possibility of extraterrestrial life. The balance of gases in a planet's atmosphere is crucial for maintaining conditions suitable for life. Understanding atmospheric composition aids in the search for habitable exoplanets. Kepler 186 is an exoplanet located approximately 500 light-years away from Earth. The exoplanet Kepler 186 is about 1.2 times the size of Earth. Kepler 186 orbits a red dwarf star within its habitable zone. Due to its size and location, Kepler 186f is considered a potentially habitable planet, although its atmosphere remains unknown. Proxima Centauri b is an exoplanet orbiting Proxima Centauri, the closest star to our Sun. The exoplanet Proxima Centauri b is slightly larger than Earth. Proxima Centauri b lies within the habitable zone of its star. The exoplanet is subject to strong stellar flares due to its proximity to a red dwarf star. Stellar flares could significantly impact the habitability of Proxima Centauri b. The close proximity to its star results in Proxima Centauri b being tidally locked. TRAPPIST-1 is an exoplanet orbiting the ultra-cool dwarf star TRAPPIST-1. The exoplanet TRAPPIST-1e shares similar size and mass characteristics with Earth. TRAPPIST-1e is located within the habitable zone of its star system. Scientists hypothesize that TRAPPIST-1e may possess liquid water on its surface. The potential presence of liquid water makes TRAPPIST-1e a promising candidate for harboring life. GJ 1132b is an exoplanet orbiting a red dwarf star. This exoplanet possesses a thick atmosphere that has been detected and studied by scientists. Although too hot to be habitable, GJ 1132b offers valuable insights into exoplanet atmospheres. Studying GJ 1132b helps scientists understand the composition and dynamics of exoplanet atmospheres. Research on exoplanets like GJ 1132b advances our knowledge of planetary formation and evolution. A planet's size influences its gravitational pull and ability to retain an atmosphere. Planetary mass affects internal geological activity and the potential for volcanism. Density is a key factor in determining a planet's composition, whether rocky, gaseous, or icy. A planet's rotation rate influences its climate and the distribution of temperature across its surface. The presence of a magnetic field protects a planet from harmful solar radiation. These factors collectively determine a planet's climate, geology, and atmospheric retention, impacting its overall habitability. A planet's magnetic field protects it from harmful solar wind and cosmic radiation. Without a magnetic field, a planet's atmosphere can be stripped away by solar wind. The loss of atmosphere makes it difficult for life to exist on a planet. Planetary magnetic fields are generated by the movement of electrically conductive material within the planet's interior. Earth's magnetic field is crucial for maintaining its habitable environment. The strength and configuration of a planet's magnetic field vary depending on its internal structure and rotation. Scientists are actively searching for biosignatures in the atmospheres of exoplanets. Biosignatures are indicators of life, such as specific gases present in a planet's atmosphere. Oxygen, methane, and phosphine are examples of gases that could be produced by biological processes. The presence of biosignature gases can suggest the potential for life on an exoplanet. Advanced telescopes and spectroscopic analysis are used to identify these biosignature gases. The search for biosignatures is a key step in determining the habitability of exoplanets. Future space missions aim to provide detailed observations of exoplanets and their atmospheres. The James Webb Space Telescope will contribute to exoplanet observation. The extremely large telescope will also enhance exoplanet observation capabilities. Detailed atmospheric observations help assess exoplanet habitability. Scientists search for signs of life in exoplanet atmospheres. Advanced telescopes enable a better understanding of exoplanets and the potential for extraterrestrial life. The search for habitable exoplanets is an ongoing scientific endeavor. Scientists continually discover new exoplanets using advanced detection methods. New methods are being developed to assess the habitability of exoplanets. Research aims to determine whether life exists beyond Earth. The exploration of exoplanets brings humanity closer to understanding its place in the universe.